Hello everyone, welcome to Robert Morris University Math 0900, Chapter 3, Lesson 2. This is Brianne Pernick. We are going to start working on the lesson that teaches how to use equations to solve word problems. There are no new vocabulary words for this section. And what we're going to begin working on here are problem-solving strategies that are going to help us organize the material that's presented within the word problem so that you can use it as a guide as you solve through the word problems. Now, the strategy that I use myself and the strategy that I teach as we're solving word problems is called the guess strategy, and we don't actually guess the answer to the word problems. What guess is an acronym that stands for the given information, and what you do during this step is identify what information has been given to you during the problem. Next, we identify the unknown information, and that's where we write a let statement that defines our variable or variables if there are two things that we have to find. Two or more things, I should say. After that, we would write our equation, and that is the equation that we would use in order to solve the problem. The first S is solving the equation, and in this step you want to be sure that you are showing all of the work. And then lastly, the last S is writing a sentence. The sentence that you write should answer the original question or questions that's presented within the word problem itself. I like the guess strategy because it's a nice, easy word to remember, and each letter of that acronym helps you to remember an important process of the word problem solving strategy. Now, I do want to point out to you that your textbook that we're using for this course teaches what they call the mathematics blueprint. And the mathematics blueprint is a chart that allows you to organize facts, determine what to set your variables equal to, and select a method or approach that will assist you in solving the problem. It's very similar to the guess strategy that I use, but it's just a little bit more visual. And if you are a visual learner that requires that type of chart or something like that, you might prefer the mathematics blueprint because it helps you organize your information into that chart. Whichever strategy you choose, just some important things to remember are the following. You always want to make sure that you are understanding the problem. So you have to read the whole problem carefully to get an overview. Determine what information you will need to solve the problem. Draw a sketch if necessary. Label the known information. Determine what needs to be found. Choose a variable to represent the unknown quantity. If necessary, represent other unknown quantities in terms of that very same variable. Don't ever introduce a new variable. Remember, at this point, we only know how to solve problems with one variable in them. Step 2 is write an equation. You're going to look for the key words to help you translate the words into algebraic symbols and equations. And we're going to use a given relationship in the problem or an appropriate formula to write an equation. Step 3 is to solve and state an answer. And step 4 is to check. Check the solution in the original equation. Is your answer reasonable? And B, be sure that the solution to your equation answers the question in the word problem. You may need to do some additional calculations if it does not. So what we're going to do now is look at some examples. Example number 1 says 2/3 of a number is 84. What is the number? Well, the first thing that we're going to do here is write a let statement to represent our variable. We're solving for a missing number, so we're simply going to say that we're going to let n represent our missing number. So we know that 2/3 of our number, of indicates multiplication, so 2/3 of a number is indicates equal, 84. We have just written an equation. We're now ready to solve. To undo the multiplication of a fraction, the easiest way to get rid of that multiplication is to multiply by the fraction's reciprocal. So we're going to multiply both sides by 3/2. When we do so, that's going to cross cancel everything on the left hand side. And on the right hand side, we will find that n equals 126. N equals 126. So we would go ahead and write the final answer here as the number is 126, because we always want to answer every word problem with a sentence. Example 2 is another number problem. And it says 5/6 of a number is -35. What is the number? So we're going to write another let statement. Let n equal the number. We have 5/6 of the number equals -35. To undo the multiplication of a fraction, we want to multiply both sides by the fraction's reciprocal. So we'll multiply both sides by 6/5. We will allow the cross canceling to happen on the left hand side. We can cross cancel on the right. 5 will become 1, 35 will become 7. So -7 times 6 is -42. And we would finish off by saying the number is -42. Example 3 is an example where we will be finding two missing numbers. It says the larger of two numbers is 3 more than twice the smaller. The sum of the numbers is 39. Find each number. What we have to look at here, since we're being asked to find two numbers, is we have to make a determination of which number is based off of the other. Is the larger number being based off of the smaller, or is the smaller being based off of the larger? So we're going to go back to our first sentence. It says that the larger is blah, 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 the smaller. So that tells us right here that the larger number is based on the smaller. Since the larger number is based on the smaller number, when we write our let statements, we can let our variable, and I'm just going to use x, represent the smaller number because it's going to be our starting point. So I'm going to let x equal my smaller number. I am now ready to write a second let statement that's going to represent my larger number because I'm being asked to find both numbers. So I'm going to go back to my very first sentence where it says that the larger number is 3 more than twice the smaller. Twice the smaller number can be represented by 2x, and 3 more than that would be a plus 3. Now that we have an expression for both the larger and the smaller number, we can now focus on writing the equation. The second sentence in our problem tells us that the sum of the numbers is 39. That means that the larger number plus the smaller number is going to equal 39. So putting that in words, the smaller number plus the larger number is going to equal 39. That's what's going on there when they tell us that the sum of the two numbers is 39. So at this point, we can make a substitution using the expressions that we wrote in our let statement. My smaller number is being represented by x, and I'm going to add that to my expression that I wrote for my larger number, which is 2x plus 3. And that is all equal to 39. We can now combine like terms. X plus 2x is 3x, plus 3 equals 39. We're going to subtract 3 from both sides. 3x equals 36. Divide by 3, and x equals 12. We have solved for x, which gives us the value of the smaller number. In order for us to find the larger number, I must plug my value of 12 into the expression of 2x plus 3 so that we can find the value of that larger number. So 2 times 12 makes 24, plus 3 makes 27. So that tells me as I write my sentence that the smaller number is 12 and the larger number is 27. I would like for you to try example 4, which is very similar to the one that we just did. Please pause the recording and try this problem. Whenever you're ready, please press play and we will try the problem together. Okay, at this point you should have had an opportunity to solve example 4, and you should have noticed that when it said one number is 15 less than 7 times the second number, that meant that the first number is based off of the second number. So we're going to let x equal the second number. And then when we write our let statement, we can refer back to that very first sentence that says one number is 15 less than 7 times a second number. So 7 times the second minus 15 equals the first number. So that's a 15 there. I had put my equal sign just a little too close. So 7x minus 15 will be the expression that we're going to use to represent our first number. The sum of the numbers is 73. When I add my two numbers together, it will equal 73. So I want to use my x and my 7x minus 15 and add them together. So x plus 7x minus 15 equals 73. Combining like terms, x plus 7x equals 8x minus 15 equals 73. Add 15 to both sides, and 8x equals 88. Divide both sides by 8, and x equals 11. Now, when x equals 11, that simply told me my second number. In order to find my first number, I must plug my 11 into the expression 7x minus 15. 7 times 11 is 77. 77 minus 15 is 62. So now that we know both of the numbers, we can write a sentence that says the first number is 62 and the second number is 11. The second concept that we're going to look at today is using our problem-solving strategy that we've just been working on to solve applied word problems. So we're going to be doing exactly the same thing. We're still going to write let statements and equations and solve them and write sentences. But this time, instead of just having number problems where we're looking at the relationship between numbers, we're going to have given situations. So our first problem says that the mean annual snowfall in Juneau, Alaska is 105.8 inches. This is 20.2 inches less than 3 times the annual snowfall in Boston. What is the annual snowfall in Boston? As you're reading this, we're going to focus on the second sentence. It says, this is blah, 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 than blah, 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 Boston. So the number that was given for Juneau is based on Boston. Okay, so that tells us that Juneau is based on Boston. So Boston has to be our starting point. So we're going to let B equal the snowfall in Boston. So now that we know that our starting point is Boston, what we want to do is come up with a statement that's going to represent Juneau. We know that Juneau has a total of 105.8 inches. And we also know that the 105.8 inches is equivalent to 20.2 inches less than 3 times the snowfall in Boston. So if we can write an expression in terms of B according to this information that we were just given that represents Juneau, we will be able to solve for the snowfall in Boston. So it tells us, let's start with the 3 times the snowfall in Boston. So we have let 3 be, and then we have 20 less than that, minus 20.2. That expression right there represents the snowfall in Juneau, which we were also told is equivalent to 105.8 inches. So we wrote an expression that represented Juneau's snowfall, and we happen to know exactly how much that expression is equal to in inches because the problem told us that. Now all we have to do is solve this two-step equation. So we're going to add 20.2 to both sides. So 3b equals 126. Divide 3 on both sides. And we see that b equals 42. What does this mean? We solved our equation. What does b represent again after all this work that we've just done? Refer back to your let statement. That's why you wrote it. B represents the snowfall in Boston. Does that answer our question? It should. That's why we wrote that let statement. Boston receives 42 inches of snow. Example 6 is fairly similar. I would like you to take a look at this problem, try to solve it on your own, and as soon as you're ready, come back together and we'll go over the answer together. Okay everyone, by now you should have had an opportunity to solve example 6. It says that the maximum recorded rainfall for a 24-hour period in the United States occurred in Alvin, Texas on July 25th through 26th in 1979. The maximum recorded rainfall for a 24-hour period in Canada occurred in Euclid Brenner Mines, British Columbia on October 6, 1977. Alvin, Texas received 43 inches of rain in that period. The amount of rain recorded in Texas was 14 inches less than 3 times the amount recorded in Canada. How much rain was recorded at Euclid Brenner Mines in Canada? So we're going to focus on the question, since that's what we want to solve. We are going to let x equal the amount of rain in Canada. You always want your let statement to refer back to what the question is asking you. Note in the problem that we solved before that our let statement directly referred to the question that we were being asked. So our let statement here is going to answer the question that's being asked of us. And now we're going to go back into the problem in order to help us write the equation. We know that Alvin, Texas received 43 inches of rain, and that number was 14 inches less than 3 times the amount recorded in Canada. So in Canada, we're saying that it was X, and in Texas, that was 14 less than 3 times Canada. So 3 times Canada, and I want 14 less than that. And that will equal what was received in Texas. They told me that Alvin, Texas received 43 inches, and then they also told me that the amount of rain in Texas was 14 inches less than 3 times the amount recorded in Canada. So I have an expression equivalent to Texas, and I have a total equivalent to Texas. Because my expression represents Texas, and because my amount represents Texas, they are equivalent, and I'm allowed to set them equal to each other. We can now solve the equation and add 14 to both sides. So 3x equals 57. Divide both sides by 3, and x equals 19. So that means that the Euclid Brenner mines received 19 inches of rain. Okay, the next section that we're going to talk about here, and this is the last little section within chapter 3, section 2, talks about using using formulas in order to solve word problems. So example 7 says that 2 people travel in separate cars. They each travel a distance of 333 miles on an interstate highway. To maximize fuel economy, Fred travels at exactly 50 miles per hour. Sam travels at exactly 55 miles per hour. How much time did the trip take each person? So what we want to do first here is think about what formula we want to use. Since we're talking about distance, speed, and time, we do want to use the distance formula, which is D equals RT. And we're going to be setting up 2 different formulas, one for Fred and one for Sam. So let's do Fred first. Now their distance is exactly the same, so we're going to plug 330 in for the distance, and Fred was traveling at 50 miles per hour. So we need to solve for his time. We will divide both sides by 50. 330 divided by 50 gives us 6.6. So that tells us that his time was 6.6 hours. We'll just hold on to that number for a minute. And now we'll talk about Sam. We have D equals RT. He drove the same distance, 330 miles per hour, but 330 miles, but he drove 55 miles per hour. So we'll divide both sides by 55. 330 divided by 55 gives us 6 hours. So we can say, as we write a sentence, that the trip took Fred 6.6 hours and Sam 6 hours. However, you may have a professor that does not want your answer as 6.6. Excuse me. Because think about it. You don't walk around and say, I will be at your house in 6.6 hours, or I will arrive at your house in 2.2 hours. We say things like, I'll be there in 3 hours and 15 minutes, or 2.5 hours. To use a decimal doesn't make logical sense to people. So you most likely are going to have to convert your decimal value of that hour to minutes. Okay? If your directions don't specify, you could probably get away with writing your sentence like that, and it would be okay. But if the directions do tell you to convert to hours and minutes, you will need to take your 0.6 and multiply that by 60, because there are 60 minutes in an hour, and you will find that that is 36. So that means that it took Fred 6 hours and 36 minutes to drive 330 miles. And that probably makes more sense to you than 6.6. Sure, we could look at that and say 6.6 is close to 6.5. And then now that you're looking at that and saying 6 hours and 36 minutes, it's probably easier to see that it's close to 6.5. But please keep this in mind, that you may need to convert your decimal to minutes at some point in your future, and you must need to know how to do that. Okay, let's look at example 8. Example 8 says that Sarah left the city to visit her aunt and uncle who live in a rural area north of the city. She traveled the 220-mile trip in 4 hours. On her way back home, she took a slightly longer route, which measured 225 miles on the car odometer. The return trip took 4.5 hours. What was her average speed on the trip leaving the city? So again, we're going to work with the distance formula. D equals RT. And we want to know her speed. So why don't we manipulate our distance formula here and solve it for the rate, since we are solving for speed in this formula. Go ahead, pause the recording, solve for speed, and then go ahead and hit play again. Okay everyone, by now you should have solved your distance formula for R, and in order to do so, you would want to divide both sides by t, and you would have that r equals d over t. The reason that you would want to do that is because now your r is isolated, and you would be able to see that you can simply take your distance of 220 and divide it by the time that it took her to drive that, which was 4 hours, and then your answer would be 55. So Sarah drove 55 miles per hour. So now what was her average speed on the return trip? We can use the formula that we already solved for r, d over t, and plug in her return distance and her return speed. Go ahead and pause the recording. When you're ready, go ahead and press play and we'll go over the answer. Okay, for part B, you should have plugged in that she drove 225 miles on the way home and her time was 4.5 hours. So her rate was 50 miles per hour. So Sarah drove 50 miles per hour on the way home. So part C, on which trip did she drive faster and by how much? We can see that she drove faster leaving the city by 5 miles per hour. Because she drove 55 miles per hour, and on the return trip, she drove 50 miles per hour. Okay, our last example here is example 9. And in this example is actually a very common algebra problem, and you will see this type of problem again, I can promise that. This one says that a teacher told Melinda that she had a course average of 78 based on 6 math tests. When she got home, she found 5 of her tests. She had scores of 87, 63, 79, 71, and 96 on the 5 tests. She could not find the 6th tests. What score did she obtain on that test? So the first thing that we want to do here is write our let statement. And since we are looking for the 6th score, we're going to let X represent that 6th score. And to write this equation, you have to think about how an average is found. When you are computing a mathematical average, you add all of your test scores, divide by the number of scores that you had, and that gives you your result. So we're going to start by taking her 5 scores that we know, 87 plus 63 plus 79 plus 71 plus 96 plus her 6th score, which is unknown right now. We will divide all of them by 6, and that is supposed to give us her average of 78 that her teacher told her. We need to add together the 5 scores that we know, 87, 63, 79, 71, 96. Adding that all together will give us 396 plus the X that we can't compute at this time, and that still gives us 78. Now please remember that I've told you that when there is more than one item in a numerator, there are imaginary parentheses around that numerator, and you cannot do anything with that numerator until it is isolated. So to isolate it, we must undo the division of 6. So to undo that division, we will multiply both sides by 6. That will cancel out that division. I'm going to go over here now. So that's going to give us 396 plus x equals 468. And now we can subtract 396 from both sides, and x is going to equal 72. That tells us that Melinda earned a 72 on her last test. If you have any questions about any of the topics that we covered in this section, please let me know. I will be more than happy to answer your questions. Thank you.